So the four main terms, you have atoms, molecules, compounds, and elements. So atoms, like I mentioned, are the actual subatomic, or not subatomic, submicroscopic particles. So the smallest particles of matter. And the different types of atoms are called the elements, which is listed underneath compounds when different elements form together by chemical bonds. But the different types of atoms are the elements, and the elements are located on the periodic table. A common for your question?
I just want to ask what you mean by submicroscopic.
Oh, so microscopic means you can see them under a microscope, such as cells, tissues, some very large polymers and compounds you could maybe see under a microscope. Atoms you really can't see under even a traditional microscope. You can't. So you can detect them with electron microscopy and different techniques like mass spectrometry. You can detect them. They're so small that you even can't see them under a microscope. That's what we mean by submicroscopic. Then you have, so here's a key or a phrase that I hear thrown around a lot, is that the periodic table has atoms on it. The periodic table does not have atoms on it. It has elements on it. It has 118 elements. And these elements are types of atoms. It's very important to make that distinction. Then you have molecules. So molecules are when any of these two atoms, regardless of their type or regardless of their elemental nature, form a chemical bond together. So examples of molecules could be oxygen gas, the gas that we breathe in, O2. Could be CO2, H2O, NaCl, salt, KCl, road salt. So these are just examples of molecules. It is the umbrella term for any two atoms that are chemically bound together. Then there is a subset of molecules. This term is called a compound. So a common thing is, for those of you or some people that don't take chemistry, maybe don't know what the difference is between a molecule and a compound. Now a compound is when you have two or more different types of atoms or two different types of elements that form a chemical bond. So out of the ones that I mentioned before, I had O2, which is oxygen gas, and I had, let's say, H2O, which is water. Which one of those is a compound, but not, or they're all molecules, which one of those is a compound? But, yeah, which one's a compound? H2O or O2? H2O. H2O, exactly. Because it has two different elements, or two different types of atoms that compose it. So these are important fundamental terms. Okay, so another really important fundamental thing about chemistry is the scientific method. And this is, I'll go on a little bit of an aside. So today's world is crazy. I'm never gonna get into politics with this class, in any class, but like, you know, fake news is always like, you see like the Onion, right? You know, like those fake news sites and stuff. And there's a lot of like, not fact, there's a lot of information that may appear as fact thrown out there, but it's not fact. So as scientists, as engineers, as smart people, here's what we can do to defend ourselves and defend the truth against these opposing lying forces. The scientific method is our weapon. And the scientific method, it starts out with an observation. So speaking scientifically, you observe a natural phenomenon, let's say it's natural, and then you have an idea of what could cause this natural phenomenon. So let's use Isaac Newton as an example with gravity. So Isaac Newton saw stuff fall from the sky, whatever, he dropped an apple, whatever. He was like, all right, what is the force that's causing this to happen? So he can have a number of hypotheses that they could all be tested, and they could all be, they're valid hypotheses, doesn't mean they're true. So an example, let's say he thought the apple had magnetism or had metals in it, trace metals that were drawn to the Earth's core because the Earth has iron in it and it's a magnet. Not a good hypothesis, we know, but for the time it could be. And then he can be like, all right, there's some other force that's dragging it to the ground, or he could say that there's this big invisible cyclops that has a hand and it comes up from the Earth and it takes the apple and pulls it to the Earth. That's a hypothesis as well. They're just educated guesses and explanations for phenomena. But these hypotheses can be tested. And once you test them with an experimental technique that good experiments are really have no confounding variables or everything that can possibly happen is accounted for, then you come to conclusions and you come to real world conclusions. So what Isaac Newton can do is he can take an apple, he can drop it, then he can take something that we know is not magnetic, such as a brick. Let's say if you can get a brick of helium. Helium is very inert, doesn't react with anything. You get helium, what's it going to do? It's going to drop to the floor as well. If it's a brick of it, it's in a solid form. It's going to drop as well. So that means, all right, the Earth does not have a magnetic pull to things at all. I mean, it's because we know something that's not magnetic also falls down to the Earth. It's not a cyclops because you could do a bunch of experiments to see there's no cyclops in the Earth. So then you come to the conclusion it's some other force. And then we later learn that, all right, there's this huge ball that we live on that it bends space-time and it has its own gravitational field. And that gravitational field pulls everything towards it. Everything that's smaller towards it. And then there's a bigger ball called the sun and it pulls us towards it. So that's how we go from a simple observation to a hypothesis, test hypotheses, and multiple hypotheses to make a theory. That theory goes into a law. So I'm not going to really stress this too much, but it's important to understand the process that scientific observations and scientific experiments and conclusions are, for the most part, they're the best examples of truth that we have. Even though sometimes laws get broken, some scientific laws of physics that are fundamental things of kinematics. When you go near the speed of light, they get thrown off and all of our laws of physics become out of whack. But this is just expanding on the law. It's true for a certain case, but for other cases, it's not. So this is how we learn it. Okay, so anyone can just call out whatever. So my car, for this one of the three. So my car has starting trouble, has starting trouble. Yeah, car started. Shouldn't it say trouble starting? Yeah. My car has starting trouble on cold, wintry days. Is that a theory, hypothesis, or an observation? Observation, good. So that's just an observation, you observe it. My car has a starting problem on cold days because of a faulty spark plug.
A theory?
Hypothesis, good. Because that's your idea about why it could be. Then it appears that all the models of the Juno cars from 2010 had the same problem. There was a faulty spark plug that installed this year. And that's a theory, right? So the only way to know that it's a law is that you get more data, you get more cars from the same year. If they all have the faulty spark plug, then that's probably the case. So good, pretty easy. All right, classification of matter. So everything's matter, everything's supposed to matter, whatever we see. Here's a good aside. So objects don't exist. If you want to know the truth, like shapes don't exist. It's just a figment of our imagination. It's just the way we perceive reality. Our mind works by sectioning things off. And that's the way our mind works for everything. With every interaction we have with every part of matter, we like to categorize things because there's no way for us to keep track of every type of thing that we see or of everything that we see. So you look at all these different, I was about to call them shelves. To me, they look like shelves, but they're seats because I'm all the way down here. So all these different seats. If I look at all these seats, I would say, they're all the same thing. They're the same exact, same everything. Yep, they're the same. But there are differences and they're each individual objects. But that's a very simple example of how we categorize things. And we do that with people too, that's not good. But yeah, it's just our way of categorizing different matter. But that's how our mind works. But in reality, everything that we know is just a soup of atoms, molecules, elements, compounds, whatever, all these molecules just bumping into each other. And the things that make the different states of matter, a solid, liquid in our body, gas in the air in our body, the only thing that makes those separations between the three states is energy. It's that's actually two things. It's the substance and the amount of energy that those particles have. More specifically, the kinetic energy that those particles have. The only thing separating really carbon dioxide and this desk is that carbon dioxide molecules have a higher average kinetic energy and they have some oxygen in them. Because this desk, if it's wood, it's made of carbon. So it's the only difference. But we see it as completely different things. So that leads me into matter. So we have state and the composition. So here's what I'm getting at, this graph up here. Yeah, there we go, this is a gyroscope. So that up there, that's important. So if we start from, and really what this is, let's go over the axes first. You have temperature on the y-axis, going from freezing cold to ice all the way up to boiling water. And on the left, or not left axis, on the x-axis, you have the heat, right? So the amount of energy, amount of thermal energy that's being put into this system. And this system, let's say, is an ice cube. So what's going to happen is an ice cube, the water molecules in the ice cube are relatively close together. They're solid. And they actually have, well, water is a bit of a different story. So if you freeze water, it actually expands. It is one of the few substances that expands. Or in other words, the volume increases. The molecules become further apart when it loses thermal energy or when it becomes a solid. And the reason why is because of the hydrogen bond. So water has very strong hydrogen bonds that are in between the molecules that kind of connect water molecules to each other. And this kind of creates what we call a three-dimensional lattice. It's like a three-dimensional structure that it has more, let's say each one of my fingers is a water molecule. It creates some kind of arrangement, a crystal pattern. And this crystal pattern happens to form space in between the molecules. This space is larger than the space in between water molecules as liquid water. So even though they're kind of rigid, stationary particles, they're shaking a little bit. Everything is really vibrating. It's still lower density and larger volume than liquid water. So that's a weird thing. But in general, we have the molecules at the low energy state, at the solid state, with that are not really moving too much. Then we're going to increase the heat. So we're going to pump in thermal energy. The temperature will go up, and the temperature will go up to a point where the molecules have enough thermal energy, or they have enough speed to break out of their solid containment and become liquid. This point is substance specific, and it's called the melting point. So melting point is substance specific because water has a different one than methane, for example. But it's all dependent on the amount of thermal energy and the threshold that substance wants, the threshold of the substance for the transition. So, and another thing that, if you go a little bit further, that determines melting point and even determines boiling point is the strength of those forces that are in between the molecules. Because think about it, what's happening when we're boiling, when we're melting and when we're boiling? We are not changing the chemical substance. If you can't boil a log, it's going to burn. That's a different process. That's a chemical process. Melting and freezing and boiling, these are physical processes, meaning the substance is being the same throughout the entire process. So liquid or solid water and ice, it's going to become liquid at a certain threshold, and then it's going to become a gas at a higher threshold. But it's still going to be H2O. And the amount of energy required for each one of those steps is purely dependent on the strength of the forces in between the molecules in that ice lattice or in the water soup, that, if you will. So that's how this works. And then, what else? That's about it. So any questions on that? So as you increase the energy, you just increase and go a little bit further, you increase the degrees of freedom of the molecules. once you do that, then you increase the kinetic energy, and then you increase the state. You're from solid to liquid to gas, the energy state. So yeah, any questions on that? No? Yes? All right. Okay, so we got that, boom. Oh, look, I said that already. Increasing freedom, to get it. Solids, not really worried about that. Liquids, we talked about that, but I'll say the definition part of it. So liquids, they have a fixed volume, not a fixed shape. So you can spill water and it changes shape, obviously. It's just pancake on the floor, but it's not going to change its volume. It's going to be a fixed volume. Unlike a gas. So gases, they have this really unique property of being compressible, which means when we talk about gases in chapter 8, I think, or no, 7, maybe 7, maybe 10, I don't know. It's either 7 or 10, not 8 or 9. But regardless, we're going to be talking about gases at some point in this class. And when we do, we're going to be introducing this unique property of pressure. And pressure has to do with the compressibility, or really it has to do with force. The force that these gas molecules are being put on, or that are putting on, or the force that the gas molecules are putting on the container that they're in. Sorry, I've been up for a while. I've been exhausted. So, for example, you see a piston there, and let's look at the right one first. Let's look at the left one. Oh, it's a solid. You put it in, it doesn't compress. Oh, whatever. But let's look at the right one. I'm pointing at my screen like an idiot. The online people can't see that. So let's look at this one. So gas is compressible. So as you push this piston down, these gas molecules are going to have less places to move. So they're going to move faster. They're going to bounce off the sides of their container faster. And what that does is that increases their speed. And increasing their speed means it increases their force on the container, which means it increases their pressure. So the more you compress a piston, the higher the pressure is. And that's called Boyle's law. It relates pressure and volume. So at the same time as we're compressing that piston, we are decreasing the volume, and in turn, increasing the speed of the particles because they're hitting against the sides of the container faster, and increasing the force because they're increasing the speed, then increases the force. And then the definition of pressure is the force per unit area of something being put on something. So if you're decreasing the volume, you're directly increasing the pressure. So that's how that works. That's like one law, but we're going to be learning a whole chapter on that. But if you didn't follow that, no big deal. I didn't even follow what I just said. But yeah, so they're compressible. Cool. Okay, so here's just a summary of solids, liquids, and gases. Also, solid gases, they occupy the entire container. And it's a good thing they do, because if they didn't, then if you farted, you'd be able to, it would like travel like in the same unit of space, and it would just move. And you'd be able to smell it like an hour later if somebody walked by. Yeah, I have terrible jokes like that, whatever. But I mean, it's also true, like the fact that when we fart, it expands and goes the width of the classroom, that's good, because it takes the volume and there's only there's very small particles of it, nitrogen gas and sulfur gas maybe, that are so expanded in the room that we can't smell it anymore. That's good. So I've been rambling about nonsense. I want to talk about something cool first. Now, also we're going to take a break in the middle. We're going to take a break in like 10 minutes. Oh, I got a lot of missed calls. Unpopular. Cool. All right, so about gases. You have air, right? The air is composed of oxygen gas, nitrogen gas, a little bit of hydrogen gas, some CO2, and some argon gas. These gas molecules are moving very rapidly. Does anybody have an idea of how fast they're moving? Kind of a weird question. Something that nobody really thinks about. Okay, I'll just tell you. They move at 0.5 kilometers per second as their average velocity. Think about that. That is from here to the other end of campus in like a second. So That's crazy. Now, for something moving that speed, that is just around us all the time and fills up the air, how come we don't feel it? Can you say that again?
They're too small.
So good thought. That's a common answer, that they're too small, that we don't feel them. But there's so many of them that, I mean, if they gang up on us, we should be able to feel it, right? But there's another reason why we can't feel them, or are we just used to them, something hitting us at that speed, millions of them at once? I wouldn't be used to that. But, so yeah, you have an idea?
That's because they're bumping into each other.
Exactly, good. So it's because they're bumping into each other. And the amount that they're bumping into each other, we can't even fathom these numbers. So if you took chemistry in high school, you're familiar with the mole. There is hundreds of moles of them in this room. And they are going this speed over a distance of, at most, a millimeter or a few micrometers until they reach another gas particle and hit it. And then they bounce off, and they do it the other way, and they boom, 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 like a big ball pit, ping pong, pinball, I guess. Yeah, pinball with like 50 of them, imagine that. So that is what it's like. Now, and then all the net motion cancels out. So there is a case where we do feel them, and they can actually kill us. Anyone have an idea?
It's like wind.
Yes, was that your idea?
Yeah, I was gonna say pressure of the gas.
Pressure of the gas and wind, both correct answers. Because what causes wind? A pressure gradient in the atmosphere from high pressure to low pressure that forces the gas molecules to go from high to low really quickly. And it kind of coordinates all of the gas molecules to go in one direction. And if it's fast, if it's a large pressure difference, they'll hit you at a really high speed, and then you might die in a tornado or something. So, ta-da, that's it. Okay, so last thing we'll do before our little break is we will break up the classifications of matter. Now, all matter can be broken up into these two categories called pure substances and mixtures. A pure substance can be broken apart into these two types of pure substances, an element and a compound. Now, you might be wondering, where's a molecule? A molecule is under compound, or a molecule is under both of them, really. A molecule technically counts as a pure substance. Because, so an element is just an elemental form of something. So on the periodic table, you have gold, you have hydrogen, you have a lead, right? A brick of lead is in its elemental form of lead. So anything that's just an elemental form, that's that. Also, oxygen gas is in its elemental form. Because it's just it's the way oxygen naturally arranges in a diatomic gas. Something like hydrogen gas, nitrogen gas. Those are all diatomic gases. And that is considered to be, in a natural environment, their elemental form. And then you have compounds. So compounds are like we talked about before. You have salt, you have water, you have sugars. Really, is an infinite amount of compounds. And there, if you have a pure substance, let's say deionized water. So take all the ions, all the sodiums, all the fluorines, all the chlorines out of water, you have this pure H2O as every single molecule. That is a pure substance. And then on the mixture side, you have homogeneous mixtures and heterogeneous mixtures. So a homogeneous mixture has the same composition throughout the entire thing. So this example they use brass. I think this is brass. So, or even bronze, even if it's bronze, it's still homogeneous. But basically, you are, let's see, so what does it make? Bronze, you have tin and what else? Copper, yes, copper and tin. I learned that from RuneScape back in 2007. So yeah, copper and tin makes bronze. When you mix those together, it's not like a salad where you can pick like lettuce and pick a crouton or whatever. It is a homogeneous mixture. You are smelting them together. So you're going to mix them so well that all the molecules are fully dissolved in one another. So it's a purely homogeneous mixture. And then you have heterogeneous mixture, which anything that really everything is a heterogeneous mixture that you can think of. Our bodies are heterogeneous mixtures. There's tissue, there's skin, there's organs and everything. It's not homogeneous, not the same throughout. So here we have, what do we have? Sand and rocks and stuff, and some gold in there. Yes, a salad. Really, there's endless examples of heterogeneous mixtures. So yeah, any questions on that? And those classifications? You want to, there's actually not to confuse you, but in reality, everything is heterogeneous. And the reason why is because, let's say you get an element or a compound or a homogeneous mixture. You look closely, you have different isotopes. And isotopes, we're going to talk about that, I think, next week. That's the reason why everything is heterogeneous. But if you take it at a large enough scale, it's considered to be homogeneous. Let's say hydrogen has 3 isotopes. Tritium is 1 out of every 10,000 atoms of hydrogen. So if you take a scoop of it, even a little pinch of hydrogen, of tritium, it's going to have, well, you get radiation. But if you don't die from radiation, it'll still be considered to be homogeneous. Yeah, so, or considered to be a pure element. Okay, so I've been talking too long. We are going to, right here, take a little break. Okay, let's continue. All right, so. Okay, so next thing we're going to learn, again, not a really difficult skill, is the different changes in matter, right? So you have a physical change and a chemical change. We already talked about one classification of physical changes where it changes the state of matter that we're in, such as going from solid to liquid to gas. That is a physical change because the type of molecule or the chemical substance is not changed at all. When you're going from ice to water vapor. So composition not changed. When you have a chemical change, it is directly changing the composition. You are either destroying one molecule, breaking up bonds, and making new molecules, or taking a bunch of molecules, smashing them together, and making a larger molecule. So examples here, they have sodium metal and chlorine gas make sodium chloride. Sure. Easiest example I like to use is combustion. If you're burning this table is carbon. You are putting high energy oxygen, which is fire, and you are creating CO2 and H2O. That's all that's coming out of it. So you can't really put that back together, and ashes and heat. So you can't really put all that stuff back together without doing more chemical processes. Whereas if I took a piece of paper, if I took a piece of paper and ripped it in half, each part of it is still paper. I could easily put it back together to its original shape, doing a physical change rather than doing a chemical reaction. So those are the differences between those two. So water boiling, chemical changes, some key words to know if it's a chemical change. You have burning. In this case, we have rusting. Rusting is a form of oxidation, where you have metals like iron exposed to the elements, and the main element that's exposed to that causes this rusting is oxygen. So oxygen from water, mostly water, and then you have just the air itself. They will actually stick to the oxygen and create iron oxide. This iron oxide has this rusting. That's how rusting happens. So yeah, there's a chart of physical changes. I always have to look at the chat. Oh, here we go. All right, so this is random, but making a smoothie, would that be chemical since it can't? Good question, but that's a good question. It can be reversed. What? Yeah, it can. So think about it. It's the same principle as salt water. I could dissolve salt in water. Can I reverse that process physically? Yeah. I can boil out the water and you end up with the salt using separation techniques. So a smoothie, let's say we have, what do you put in a smoothie? Name smoothie ingredients. Strawberry, a mango. Okay, fruits. You have milk, right? Ice, and you have ice cream.
Yeah, for sure.
Yeah, ice cream and some whipped cream on that. Yeah, I'm getting hungry. What'd you say?
For sure.
For sure. All right. Okay, all these ingredients. All of those different ingredients have specific chemical properties and physical properties that make them different from one another. I don't know off the top of my head how to remove all those, but simple experiments such as distillation. We can distill out the water. We can boil out the water because, but really, the thing is, once you mix it up, so the mango or any fruit, you're having it's kind of like it's a seed. It's an organ think of it as like an organ. It has all these different molecules inside of it that are not chemically bound, but they're doing things. They're the cells. They're working around in their inside. But with a blender, you're blending those up. You can't make the mango again, but you can get every single component that was in the mango in its same chemical form. And technically, you could put it back together. So let's say the mango had water, it had amino acids, it had vitamins, it had macromolecules, it had some fats, some lipids, some carbs, some sugars. You can, from the smoothie, you can extract with different extraction techniques and separation techniques those different molecules and put them in different containers and put this mango back together. Technically. So yeah, it's possible. You're wrong. Okay. But yeah, that's a really good question. I actually I use smoothies as an example for chemical changes or physical changes I use it for homogeneous or heterogeneous mixtures and physical changes for like 4 years now, and no one's ever said you can't put it back together. But good question. Yeah, so another one that is like getting on foods is baking a cake. If you bake a cake, that is a chemical reaction. That is a chemical change. You can't unbake the cake because when something like batter, it rises. The reason why it rises is because the heat causes chemical bonds to break in the dough, and those chemical bonds expand the volume of the dough, and when they break and form new bonds. So you can't undo that without doing more chemical reactions.
I think this is extremely useful. With the sugar dissolving, isn't our chemical bonds
So no, sugar dissolving is a good question. So his question was, in sugar dissolving, aren't bonds being broken? So sugar and salt dissolve differently. Sugar, and they're both, we'll learn about polarity later, but they're both polar molecules. They have charges on them. So water has two charges. It has a negative pole and a positive pole. So the positive end is the hydrogen, negative end is the oxygen. So once water, what it essentially does is it attacks the sugar. So the negative ends of the water, meaning the oxygens, will attack and engulf the positively charged ends of the sugar, and then vice versa with the other charges. That will completely engulf the sugar and make it one with the water. And you can undo that process by boiling out the water. So that's a good question.
So with salt, isn't it for the
Yes. Still no, because what happens when you boil out the water? They go back together. So, good questions. So his other follow-up question was, with NaCl, like salt water, isn't the Na being broken apart from the Cl to dissolve in the water? And that's exactly right. But when it's being broken apart, it is not being formed into a new chemical substance. So water is not making a permanent chemical bond, ionic or covalent, to the NaCl. It's making an intermolecular force of an ionic attraction. Really, it's a dipole ion, if you want to be specific. But that force is not making a new molecule. It's just an attractive force. Then once the water gets boiled out, they go back. Good question. Okay, so energy and work. You know what, we'll just go quickly with this. So there's two types of energy, because I want to get to the unit conversion to me. So energy, there is Kinetic energy and potential energy. Kinetic energy is the energy of motion, which most of you are taking physics, right? You're freshmen, so yeah. So energy of motion, 1/2 mv squared, that's kinetic energy. So potential energy is the other form of energy, and it is the energy associated, really, the way I think of it is the potential to become kinetic energy. So it is the energy associated with the position of something. Let's say if I hold this high up, this has more potential energy than here. Because once I remove the force that is keeping it in the air, which is my hand, it will fall to the ground. And the equation for that is mgh. So it depends on the height. It depends on the height from the ground. So that's potential energy. It's just, and that potential energy can be stored. So in this case, the energy is stored in the object and in the height of the object. Potential energy can also be stored in food, in the bonds of the food. When your body breaks down those bonds, energy is released, ATP is created, and it's used for your metabolic process. Sorry, my voice cracked. I'm really thirsty, but if I pass out, you can just go. There's no point. So yeah, potential energy. Something I like to say is, you guys all have potential to get an A in this class. Somebody dropped the link to the group meeting, so that's cool to do that. I won't go near it. If you Zoom bomb me, I'll group meet bomb you. I'll get someone else to do it. Okay, so you all have the potential energy to get an A in this class. I want to see you turn that into kinetic energy by studying. Okay. Okay, so intensive. Now these are just more definitions. You can tell this chapter is kind of just a conglomerate of different ideas. Just kind of setting the stage. So an extensive property, well, we'll go an intensive property. So whenever you have the prefix int, it usually means something, in chemistry at least, something to do with the substance. So in my field of chemical biology and cancer drug discovery, we talk about intrinsic things a lot. So the word intrinsic means it's something that is a trait of the substance or the protein or the cell. It's intrinsically happening. It just happens automatically. It depends on that substance. It's always happening. So an intensive property is very similar to that. It depends on the substance, not the amount of substance. So, for example, boiling point, temperature, and density. Now, the boiling point, the temperature, and the density of water does not depend on there. So you dropped the group me link. You guys, you're blaming me for my Zoom links, but you can't get your group me links to work. So that's an intensive property. Something like boiling, like something like water, it doesn't depend on the amount. The boiling point of it doesn't depend on the amount. Then you have extensive properties, meaning just think about it as extent. The extent of the things you have, such as, and that depends on the property depends on the amount of things you have, such as the force, such as energy, such as, well, mass itself is one of them. The mass changes when you have more stuff. So I have to keep going. I have like a OCD with this. Okay, cool. You dropped the link. Nice. Okay. Any questions on that? Intensive, extensive? No? All right, let's do questions. So the work done on an object. So what work is, we kind of skipped that slide. Work is the force that you put on something over a distance. So do you think the work will depend on the amount of stuff you have? Yeah, I think so, right? Because if you break it down by equations, a lot of you guys are engineering, math thinkers. So work equals the force times the distance. Force is mass times the acceleration. So the whole thing depends on mass. So yes, that will be an extensive property. Density of a substance. Good, intensive, because it doesn't matter what substance it is. If I have an ocean of water, pure water, and I have a cup of water, the density is going to be 1 gram of water per milliliter. So it's an intensive property. Water freezes at 0 degrees Celsius. Intensive, yes. It doesn't matter how much water you have, it's always going to freeze at 0 degrees. So, good. All right, so mass and volume, we talked about that, we talked about that already. Density, important one. So, density is an intensive property, and it is the mass divided by the volume. So, very easy calculation to do. Now, unit-wise, we're going to be talking about units a little bit later, but for mass, we usually use grams or kilograms or milligrams. Those are the main 3 in chemistry. And for volume, usually milliliters or liters. We're not, in this class, we're not really going to use microliters. In my research, we talk about microliters a lot, and even nanoliters sometimes. So I'll tell you about this really cool instrument that I used when I did an internship at Merck in Kenilworth. And I did kind of the same research that I do here now. And this one instrument we used, it was the type of instrument, it's an acoustic liquid transfer device. So what it does is it takes nanoliters, like the smallest increments it could do is 2.5 nanoliters. Nanoliter, that's a billionth of a liter. And what it did was it had them in plates. Like you ever see like pictures of chemists, like they're usually taking stuff out of like these like plates with like a bunch of wells in them. Take them out of little plates, and it flips the plate over. And it flips the plate over, and you're like, oh my god, all the liquid's gonna come out. But it's so small, the amount of liquid that's in those plates is so small that gravity is outweighed by the cohesion of the molecules to the surface of the plastic. So it's not going to fall. And what it does is it puts a frequency on the bottom, the bottom side of the plate, a certain frequency that is regulated to kick out a certain volume into another plate that's below it. So it uses different resonant frequencies of the plate to kick out an amount of volume and it's finely calibrated to where you can do 2.5 nanoliters or 5 nanoliters of liquid from one plate to the other. And this thing, if you're wondering, costs like, I don't know, $600,000, I think. So you need a Lambo or a liquid handler, I don't know. Yeah, that's pretty cool. All right, density. Any questions about density? There's some units. The density of solids and liquids solids are obviously more dense on average, except for water. And it says it right there. And liquids, a little bit less dense on average, and then gases are a lot less dense than that. Any questions? No, yeah, question.
Is every lesson going to be a definition heavy?
Oh, good question. No, it's not. So yeah, this one might seem boring. It's just like stuff, more stuff, more stuff. But this is just getting your feet wet with every little concept that we're going to expand more in. Okay, density. Yeah, an example. So calculate the density of a ring with a mass of 3. Oh no. So calculate.
You're on 30.
Thank you. So calculate the density of a ring with the mass of 3.15 grams. It displaces 0.233 centimeters cubed of water. In other words, centimeters cubed is the same as milliliters. So what we're going to do is simply divide the grams 3.15 by the volume 0.233 centimeters cubed. And can someone tell me what you get? Good, 13.5. Sorry if I'm going a little bit too fast. 13.5 centimeters cubed. No, not squared, cubed. Okay, cool. Okay, so in terms of, no, I see a lot of you guys are like scrambling for notes. You don't have to, if it helps you, of course, write notes. But if I go a little bit too fast in some sections, you can see it again. It's on you. It's gonna be on YouTube, so you can see it again. Yeah. But don't go crazy with the notes. You don't have to write down everything I say, especially if I'm telling you a cool thing. You don't have to write it down. It's not going to be on the test. Only the stuff that's covered on the slides is going to be on the test. Okay. Any questions on this one? No? Move this thing down. Okay, continuing. Okay, so here's another conversion. We didn't really cover this one yet, but we will. So we didn't even talk, I don't know why they put this up so early, but we didn't talk about temperature really. So there are 3 units of temperature. There's Fahrenheit, there's Celsius, and there's Kelvin. But we didn't talk about those in depth yet. But let's say you have the conversion formula of Celsius to Kelvin. And it's very simple. Celsius is, take the Celsius temperature, you add 273.15, you get the Kelvin temperature. So if we were to do that here, what would be 40 degrees Celsius in Kelvin? You don't have to, you could just, this one's easy enough, you could just say it. C, yes, C looks right to me. Yeah, good. Good, cool. Okay. All right, moving on. So, precision and accuracy. Now, precision and accuracy in measurements are 2 different things. Now, the precision is how repeatable your measurement is. And the accuracy is how close it is to the intended value. Now, I can just read off the slides, but let's just look at dartboards and do examples. Now, the first example here is, let's say your bullseye is the target, and you've had a little bit too much to drink, or you're just really bad at darts. And you're going to do A. So A is either precise or accurate. So it's just not, if you're doing measurements and you're getting measurements that are very far off in either direction, left or right or up and down from where you want to be, that means your technique is not right, or your technique is not right and the instrument sucks. So it's a lot of, it could be a culmination of different things. Let's say B. B has precision, but it does not have accuracy. Because remember, accuracy is how close you are to your intended target. Your precision is how close you are to your other trials, so your other throws, in this case of darts. So let's say you're a very good dart player, but you had too much to drink. So you're seeing double, and you're like, whoa, which one's the real dartboard? So you have a really good shot. So you're shooting it, it's at the same spot every single time, but since you're impaired, they're all shifted to the right or shifted to the left. And they're off systematically. It's called a systematic error. So that's a good thing. That means that, all right, there's either something wrong with my technique that I can fix. Because once that fixes, that means my instrument's good enough that can detect all my values are close to each other. I can fix that and get it to where it needs to be. Or there's a setting wrong with my instrument and it's not calibrated correctly. So then shift those values over. So that's something that you can fix, a systematic error. But whereas neither the A, you can't really fix that. And then there's C, which is what you want to get, which is both precise and accurate. So darts champion. Okay, cool. Yeah, so precision versus accuracy, yeah. So it's just same thing as the dartboards, just shown in graphs. Oh, here's a question that I'm sure one of you guys are thinking. Can't you have accurate but not precise? Yeah. So, can someone give me an example? Like, what would the dartboard look like if I had accurate but not precise? Let's say it's 4. It has to be 4. So it's accurate, but it's not precise. Okay, good thought. So he said 1 in the middle and 1 and 3 like equally spaced on the outside. Yeah, so like places where 4 of them could, if you average out their positions, will equal the middle. So yeah, that's true. That's accurate, but not precise. Now the reason why they don't even show that, it is possible, but they don't even show it, is because it's not scientifically relevant. If you have a measurement that is accurate and not precise, that means your values are either way too high or way too low, but oh, their average is exactly what I need. That's called bad research. And the reason why is because those numbers have an extremely high standard deviation. They deviate from each other by a lot. So if you were to see a graph that had, so if you were to see a graph that showed this, it would look like this. So here's what, let's say you're supposed to get this as a graph. Something that is accurate and not precise would look like this. Like, oh, like it shows the right shape on average, but the noise is just so much that it's not good data. So you can say, oh, you could fit it like this, but fit it like this, and those are different things in some cases. But regardless, any questions about that? No? Okay. Okay, now moving on. Cool. Separating mixtures. We talked about that already with the smoothie example. So here's distillation. If you take an orgo, you can talk more about that. But that's one way of separating mixtures. And then filtration is another way you can separate mixtures. We're not going to cover these in detail, but yeah. So let's just continue to the important stuff. Okay, units of measurement. Now, the key units of measurement that we're going to talk about in this class is one. You know what? In every one of these charts, why is volume missing? This is the third slideshow. So I teach so many different classes. This is the third textbook that has this slide with volume missing. And I keep commenting on it every year, but I never change it. But anyway, so length. So there's the, first of all, there's the SI units. So you have the metric system, you have the US system, which is all messed up, but 12 inches is 1 foot, whatever that is. But we're used to that. And then, which doesn't make any mathematical sense for making it easy. And then you have the SI units, which is very similar and it's based off of the metric system, but it's a little bit different. Now, the SI units uses very similar units to metric, such as the meter is the base unit for length. The kilogram, rather than the gram, is the base unit for mass, but same difference. Time is seconds, of course, and then temperature is the big difference where we have it in Kelvin rather than Celsius. And we'll talk about that in a second. And then for volume, the actual SI unit for volume, I'll write this down because it is important. So the SI unit for volume.
I'm so bored.
You're bored? Oh, I'm sorry. I don't think you meant to. That's awkward. For you, not for me. That's kind of funny. I'm glad I can bore you. Now you're like, oh my God, I feel so terrible. But it's okay. No, I would get bored too. It's a night class. Listen to me ramble about gases and farts and stuff. Like, what do I do? A unit. So a unit would be, so the symbol, sometimes we use liter, but sometimes we actually use the cubic meter as the SI unit for volume. That's actually the SI unit for volume. But in chemistry, we love to use the liter. Liter is a lot better. The cubic meter is actually 1,000 liters. And yes, Hal, you're right. Volume can be derived from density, I guess. But yeah. But still, it's important to mention. Okay, so let's just continue. All right, so time is, I'll just cut to the chase. I usually ask a question, but time is the only unit that is conserved in all 3 unit systems. And that would be really weird if it wasn't, because you would have like, flights would be all messed up. You'd have different time periods. Anyway, here's a thing to think about. Every position that you are in the world is a different time zone. I'm in a different time zone than you right now. But it's by like a femtosecond. Femtosecond. Yeah, femtosecond. So it doesn't matter, but it's just, again, the things that humans make to make the things that we create to make the world easier for us. Okay, temperature. So there's Fahrenheit and Celsius, the ones we were probably the most familiar with. And here's the conversion for it. There's the equation. So I'm not going to go too far into detail. I want to get the unit conversion and really focus on that, do examples with it. That's the main skill of the day. So I do want to get to that. So yeah, so you put in the Fahrenheit temperature and minus 32 over 1.8. The 1.8, that's significant. Where does that come from? So I'm not going to have you derive the whole equation, but 1.8 is important. What that means is, if you want to break that into a fraction, 9 over 5. For every 9 degrees Fahrenheit, it equals 5 degrees Celsius. So the Celsius units are actually, each one of them carries a lot more heat with it than each Fahrenheit unit. And you can think about that as it makes sense with boiling point and freezing point of water. In Fahrenheit, 32 to 212. That is almost 200 units. Whereas for Celsius, 0 to 100. That's only 100 units. So each 1 unit of Celsius carries a lot more weight. Yeah?
Is there a particular reason behind the minus 32?
Oh, because they carry a lot more weight and they're shifted 32 units. So if you think about the freezing point of water and that Celsius is 0, Fahrenheit is 32. Shift and then convert the units. That's why the equation is the way it is. Good question. And getting into that shift, that's where Kelvin and Celsius, their conversion comes into play. It is just a shift. So I'll give you that spiel. So you have Dr. Kelvin back in 18 whatevers, a long time ago. He was like, I want to develop my own temperature scale because I want to and I'm a scientist. And he was like, his theories were, since we know at this point in history, they knew that molecules have motion and that motion causes heat and causes temperature. It's proportional. So the average kinetic energy is the temperature. That's the definition of it. So he was like, all right, what happens theoretically if you take out all of the energy of a substance, of a molecule, just one particle? What happens if you take away all the energy? What is its temperature? So he did his calculations and he was like, all right, there's got to be a point where all of the energy is removed. And he said, he found out it was negative 273.15 Celsius. This was the point at which the molecule ceases to move. And that would actually break laws of physics. So 0 Kelvin, from what we know today, is impossible because we can't stop all molecular motion. There's always some vibrational things, some subatomic vibrations going on that we can't stop. Like we can't stop the movement of electrons, for example. They're always, even if they were slowed to a crawl, it's still pretty quick. So he said this theoretical temperature is 273.15. So he was like, oh, I figured this out first. I'm going to make my own temperature unit, and I'm going to subtract all of the, or I'm going to add 273 to all the Celsius temperatures so that it starts at 0 and it goes up to infinity. That's my unit. That's what he did. So that is the Kelvin unit. Now, before that, oh, this is off. So before that, I'll give you a little temperature comparison. Now, 273 Kelvin is 0 Celsius. Think about it. 273 is 0. 0 Celsius, it's pretty cold outside, right? Freezing point of water. It's a cold winter, normal winter day for New Jersey. That's 273. The coldest temperature on Earth ever recorded was somewhere in the Russian tundra, and it was negative 122 degrees Fahrenheit. That's really cold. We can't breathe. We would get frostbite in our lungs from breathing that area. We can't go, if we show our skin to it, we can last for like maybe 15 seconds before we start to get frostbite. So in my labs, we secure our proteins in either liquid nitrogen, or when we don't use liquid nitrogen, we use negative 80 degrees Fahrenheit. And you can put your hand in there for maybe like 10 to 15 seconds before it starts to hurt. Imagine 120, negative 120. You can't stay out there. But we get it, it's cold. Okay, we get it, Professor, it's really damn cold. Oh. But that is, in Kelvin, that's 180 degrees about, 180 Kelvin. 180 Kelvin. And it's still like beyond, almost to the level where we can't survive. Then you have, let's go outer space. Let's leave the Earth's atmosphere. Right outside the Earth, you still have the sun pumping in heat. It is like 10 Kelvin out there. It's really damn cold. So if you ever want to ask yourself, okay, why do astronauts why do they wear their suits? Oh, it's radiation, solar flares will get you. No, no, no. That stuff will get you, but it'll take some time. The cold will get you immediately. 10 Kelvin will kill you instantly. So who's ever seen the movie Snowpiercer? Remember when at the beginning they put the guy's arm out of the train and his arm freezes off? That's like 10 Kelvin. But it's probably a little bit warmer than 10 Kelvin actually. But really damn cold. You die immediately. That's 10. Then you go to outer space further. Pluto. The surface of Pluto is, I think, 2 degrees Kelvin. So like single digit Kelvin, about. So you're like, all right, that's really damn, that's still gonna kill you instantly. Now, what is the coldest temperature ever that we've experienced or observed? Not including what the aliens know. They already went down this, they probably went to negative Kelvin and proved Dr. Kelvin. I don't know. But what we've observed is actually on Earth at MIT, at a lab. So what they did is they made some apparatus where they put a mango in there and they just dumped ice on it until it got really cold. No. What they did is they got subatomic particles, and I'm not sure exactly how, but they got subatomic particles. They did some thing where they opposed the motion. They had nothing to do with taking heat out. They actually figured out a way to stop, or very close to stopping the motion of particles by bombarding. That's a good word. It's a new one. Bombarding them with nearby particles until their momentums opposed each other in a way where it stopped the movement. I'm not a particle physicist, but I'm not any kind of physicist. But they got down to 0.7 or 8 zeros and a 4 Kelvin. But that was only in one particle. But they observed that temperature. And they know that's as far as we can go in our labs as of today. But the aliens, they got that thing. They're like, oh, you're only at a billionth Kelvin, we're below 0 Kelvin. Chill out, humans. Get it? All right, so, oh, good. Are you guys like the movie Snowpiercer? Yeah. Good movie. I love rebellion movies. Okay, so moving forward. Prefixes. Now, the prefixes, which you've seen most of these before, you have kilogram, you have milligram, stuff like that. To cut to the chase, the ones you need to know is everything, I would say, from nano up to giga. And good, I'm glad this chart skips the stupid ones. Like a hectometer. Hecto is 10. Deci is important. But yeah, so let's start from nano. So nano is a billionth of something. So 10 to the negative 9. So a billionth of a gram is a nanogram. Micro is a millionth, signified by that Greek letter mu. It's the only one with a Greek letter here. If those of you, are they doing Greek Russian this year because of COVID? Frats? No? Oh, you guys are freshmen, you can't do it until spring? Maybe? I don't know, whatever. I was in a frat, so that's how I know the Greek letters. But, so mu is the Greek letter for micro, it's the prefix. So you can do micrometers, for example. Then milli is not millionth, but thousandth. So millimeter, milligram. Then you have centi, like centimeter, deci, decimeter. Kilo is 1,000. So people like Breaking Bad or any drug show, like a kilo of Coke or whatever, like that's 1,000 grams of it, right? So mega is a millionth, and computer nerds like me, giga and tera, even petabytes now. You're getting into computer storage. Oh, so who knows? So I'm assuming we have some video game nerds like me. The new flight simulator for PC, Flight Simulator 2020. I don't have it, but so the whole world. What did you say?
Microsoft.
Yeah. Microsoft Flight Simulator. So the new flight simulator, they actually made the whole Earth in like really good graphics, and you can fly around the whole Earth. You can find your house in this game.
I crashed into it.
You pressed it, yeah. So like,
That's the first thing I thought.
that's the first thing you do, yeah. That's the first. I didn't get it yet. I'm gonna get it. My computer's probably gonna barely run it, but yeah, I'm really into gaming computers too. I make my own. I actually own a little company that I make them. That's doing on the side. I'll give you my card if you want later. But so this game, it's so big. It's the whole world graphically designed in this game is 2 petabytes. So you're thinking, oh, how can anyone download it? You don't download it. It's streamed. You have really fast internet connection, and as you're flying, the locations and everything spawns in front of you, right? It's like,
And everything behind you, like he's.
and everything behind you like despawns, and it kind of renders in front of you, and it streams the textures as you're playing, because there's no way any computer could hold that kind of memory right now.
So if you have like laggy internet, you're just flying over a black hole.
Yeah, if you have laggy internet, you really can't play the game. So you gotta have good internet. I'm connected on Ethernet, so also you gotta have a really damn good PC for it too. 2080 Ti's can run it at not very well, so you gotta wait for the 3000 series for that. Okay. Anyway, so any questions about prefixes as we get derailed from conversation? No? Okay. Cool. Sig figs. What I skipped? All right, that's not important, or we know that already. Sig figs. So, measurement uncertainty is an important thing. So I'll just cut to the chase because we want to get to the important stuff, which is unit conversion. That in a measurement like this, or in a measurement where you're using a graduated cylinder or any kind of measuring device that has tick marks, the way you can accurately measure it is you measure it by what you know it is, and then you guess 1 digit beyond that point. So in this case, and keep in mind this is a burette. So a burette goes from, let's say it goes from 20, and it goes negative, like it goes 20 to 21, it goes the opposite way that a graduated cylinder would. And I'll explain that in a second. But just for the measurement part of it. So this number is between 20.1 and 20.2. We know it's definitely 20.1, this measurement. But it's somewhere in the middle. So the measured numbers, they call them certain digits. Some textbooks call them measured versus estimated. This textbook calls them certain versus uncertain. The certain digits would be the 20.1. Then in every single measurement, you're allowed 1 digit that is an uncertain digit that you can guess. And from this guess, an accurate guess would be somewhere in the middle of 20.1 and 20.2. So 20.15. That would be a great measurement. 20.16 or 20.14. Great measurement, great estimates as well. So you take 5 different people and you give them this picture, and they will guess these measurements. It's a pretty accurate device that it can measure with that little small 100th degree of uncertainty. So, yeah, does that make sense? Yeah, so that's how you measure things, really. And then scientifically, that digit one, you can go 1 digit beyond the tick marks. Is what I like to say. Okay. All right, so sig figs, we just get to that. All right, any questions on anything else before we go to sig figs? All right, so not really too many questions so far, so I assume you guys you know what's up, so that's good. So sig figs. Now, a significant figure, what the hell is it? First of all, it's a pain in the ass. You have to keep track of it. But basically, it keeps track of what digits of your measurement are part of the measurement and which ones are just placeholders and not really important to the measured number itself. And you'll see what I mean in the third example. But let's do the first one where you have all non-zero digits are significant. Well, duh, that makes sense, right? If you're going to measure a number and you have numbers in it that aren't zero, you got those numbers from somewhere. You measured them. Therefore, those numbers are significant to the measurement. Same thing with interior zeros. So if you have zeros that are what we call sandwiched in between a number, like 1.05, that will be significant because you have to pass one of those zeros to get to the other one, to get the other non-zero number. So all three of those numbers would be significant. So that 1.05 will have three significant figures. Then you have the third case where it gets difficult. You have leading zeros and trailing zeros. So the rule is, let's see if we can get a better slide. Yeah. Here we go. So here's rules. So that's just, so this is 3. Don't worry about 3. Here's the zeros expanded. Same information. So the trailing zeros. So trailing zeros happen at the, well, let's start with, okay, now I'll start with leading zeros first, sorry. So leading zeros are never significant. So what a leading zero is like you see for this number right here, 0.001050. These 3 zeros in the front are not significant. They just take the place of those numbers, they're placeholders. So our device doesn't go up to that level, and it could just measure in the thousands to hundreds of thousands of place, hundreds of 100,000s place. And you can convert that to scientific notation. That's always the best thing to do for numbers with leading zeros. And here's how you would do that. 1.050 times 10 to the negative third. And this number has 4 sig figs. Even this last 0 counts as a sig fig. It's a trailing 0. But the important thing right now is that the leading zeros do not count. So any questions on that? I know I went back and forth real quick, but first thing is leading zeros do not count as sig figs. The ones in the middle of the number, the sandwiched ones, they do count. And then for the ones that are next, the trailing zeros, it depends. It depends on the presence of a decimal point. So if you have a decimal point in the number, such as 1.050, that 0, that trailing one, this one, will count as a sig fig. Because having that decimal there shows you that it's part of an active measurement that went to that degree of, let's say, sensitivity. I'm not going to say accuracy or precision because those are different terms, but the sensitivity of that number. So if a number is sensitive, that means it goes to a lot of places. Now, 1.050 is sensitive up to the 10,000 or up to the thousandth place, meaning that instrument can go that far. And that number is a 0, and it is part of the measurement. But numbers like 150 with no decimal that we have in situation B only has 2 sig figs, and that 0 does not count. And the reason why is because there's no decimal. So that 150, I'm going to write on the slide, that 150 is very similar to, let's say your beaker went from 100 to 200, and your water level was in the middle. And those are the only 2 tick marks. So a good estimate would be, all right, definitely 100, so 150. So 150 would be a good estimate. But you can't do 150.0 or 150 point because you can't tell anything about the ones place in this device. So it would just be 150, and that would be 2 sig figs. Okay, any questions about that? And the way you'd write that in scientific notation would be 1.5 times 10 to the second, like here. Now what they mean by this, if 150 has 3 sig figs, then it would be 1.50. The way 150 would have 3 sig figs, if it was 150 point. If that was the case, then you would write it as 1.50 times 10 to the second. Any questions on that? No? Make sense? Yeah. Okay, good. All right. All right, so let's go back to slides. Also, everybody online, if you have feedback from me, I really appreciate it, such as can't hear me enough, I keep moving and the voice gets distorted, or the mouse keeps moving around, or anything with your visuals that would help you receive the information better. Let me know. And that goes for everybody else as well. But I want to make it a good experience for you. This is anybody's first time doing this kind of lecturing. Okay, so There is a thing called exact numbers. So exact numbers do not require significant figures. They're not measurements at all. They're definitions, such as unit conversions, formulas, things like that, that don't require any kind of measurement. So, or counting. So for example, in this room, there's 1, 2, 3, 4, 5, 6 students. There isn't 6.00 students, there's just 6. It's a counted number. These are just a form of exact number. Then you have radius of a circle, that's a formula. So like pi is an exact number. It's not measured. No one measured pi. Well, you can't really measure pi. It exists as it is. You get philosophical here, but it exists. Okay. So another important skill we will learn about quickly, the significant figure operations. So addition and subtraction, and then multiplication and division, right? There are two different sets of operations. And there's actually different rules when it comes to sig figs, dealing with each one of these sets of operations. The first is with addition and subtraction. Now, the rule of thumb is the answer has to have the least sensitive number of decimal places as either of the numbers that are added or subtracted. So what that means is you take the weakest link out of the numbers. That is how many decimal points or decimal places your answer has to have. In this example, you see the first number, 5.74, has 2 decimal places. The other 2 numbers have 3. Meaning the 0.74 is your weakest link, your least sensitive number. So your answer must have 2 decimal places. So it's 9.21. So basically you're only as precise as your least precise measurement, or you're only as sensitive as your least sensitive measurement. Yeah, and in the next one, you have 4.8, 3.9, whatever, and then you have 1 decimal place, so your answer has to be the 1. Yeah. Make sense? Cool. Now let's do a tricky. What? Okay, so what if we had 300 plus 10? What would 300 plus 10 be in the rules of sig figs? What was that? Yeah, 300. It's weird, right? But it's 300. And the reason why is because the 10 is only significant to the tens place. The 300 is only significant to the hundreds place. So the 300 is your least sensitive number. So our answer has to be to the hundreds place. That's the nearest 100. If it was 300 plus 50, what would your answer be? 400, because you'd have to round up in that case. Okay, cool. Does that make sense? Yeah. All right, cool. That's a good. There are examples like that on the homework, so I wanted to go over that. Okay, whatever. We know how to add and subtract. Okay, multiplication and division. Another one. So multiplication and division, it's a little bit more simple. You basically take the number of sig figs of your least sensitive number, or your number. Well, it's not really least sensitive. It's you take the number of sig figs of the number that has the least number of sig figs, and you use that number of sig figs for your answer. This bullet point's better. The result has the same number of significant figures as the measurement with the fewest number of significant figures. In essence, if you have 3 numbers, one with 3 sig figs, one with 5, and one with 2, your answer will have to have 2.
Not the same thing as
Not exactly, because in multiplication and division, it talks about significant figures in the whole number, whereas addition and subtraction talks about the decimal places of sensitivity in the number. So that's a good question. So for those of you online, one of the students asked, one of your classmates asked, aren't they basically the same rule? So not really, and so here is an example. So if you added 300.8 to whatever, 300.82 plus 0.001. Let's do this. So if you were to multiply those numbers together, the 0.001 has one sig fig. So your answer would have to be one sig fig. But since we're adding, we're using the rule of the least sensitive number, which in this case is 2 decimal places. So our answer would be 300.82. That's it. Yeah, because so that one would be insignificant. So you see that there is a difference. It's based on multiplication, based on just the number of sig figs in the whole number, whereas this is just decimal points. Okay, good, very good question though. Okay. All right, significant figures we're adding to volumes, same rules. Okay, so when you're doing complex operations, now with complex operations, you're following PEMDAS, but in this case parentheses first, but you're using your rules of sig figs for every single step because you're dealing with multiple measurements. So you have to be correct in the way you add or subtract or multiply these measurements. So for the first one, you have this, in this PEMDAS, you have a 2 decimal place number minus a 1 decimal place number. So your answer is 1 decimal place, but then you're multiplying that number with a 4 sig fig number, but the number itself has 2 sig figs. Answer has to be in 2 sig figs. So yeah, it works like that. Rounding, we know how to round. Rounding and multi-step, I think we're good with that. Precision accuracy, we talked about already. Okay. So any questions before we start unit dimensional analysis from time to time? Oh, we're good.
Yeah, I have a quick question.
Yeah.
So in physics, we do this thing where if there's a 5, right, and you're rounding, and it's an odd number, then you round up, and then an even number, you stay the same. So like 3.75 would go to 3.8, but then 3.85 would stay at 3.8. So do we do that here now?
No.
Got it.
Yeah, that is actually.
That's weird.
All right.
That's not how you round.
It's going to be something with sig figs, because
Wait. So, hold on. So say that. So which one is the weird one? So say that the even one again. The last one you said.
so 3.85, if you're rounding 2 sig figs, would go to 3.8.
3.9.
Now, see that.
So you're saying 3.8?
Yeah,
Physics?
if it's even, then it stays. I was confused also, but that's how they did it in physics. So
Okay. Well, unless math changed like last night, that's not how we do
got
it.
it.
So at least in chemistry, I took all the physicses. I never heard about that either. But yeah.
I'm still kind of scratching my head under the equation you made at the bottom.
Oh, okay. Here we're adding. So we are adding. So that means we're using the least sensitive number, meaning we're using the least sensitive decimal place as our answer place, meaning the hundredths right here, under the 2, right? This is the hundredths place. This number goes to the thousandths place.
Oh, okay.
So if we add both those together,
Yeah.
in the calculator, you would get this. You get 300.821, but it'd round down.
I understand.
Okay, good. Okay. Interesting thing about the physics, I never heard about that. You'd be like, in the group meet, you can blast me, yo, professor doesn't know how to round. What the hell? But I honestly, that's weird, never heard about that. Have you guys heard about that? No, that's not how you round, right? Like this is.
I know. I was confused.
That's
also,
weird. Okay.
But that's how it rolls. And then
Wait, physics here or physics
here,
Oh, that's a roll.
yeah, Professor Roland.
Is it just him?
It might just be.
Okay. Did you guys have physics already and learn about rounding?
Yeah, I mean, yeah.
Yeah.
That's why I was confused also.
That's
So
weird, wow.
I was like, is that a thing everywhere?
You know, I'm gonna look that up. That's weird. I never heard about that. I mean, you know what? I'm gonna ask my old roommate. He's a physicist. I'll ask him. Anyway, so we did this already. Precision accuracy, we did that already. Okay, so unit analysis, the best way to teach unit conversion is do examples. So we're just gonna do examples. So I'm gonna take out my pen, and this is the good part. We're almost done. All right, so here. So convert, oh damn, this is the answer. Ignore the answer. All right, so we're converting, I'll show you how to do it. We'll convert 30 milliliters to quarts. So in any kind of unit dimensional analysis, we have conversion factors, and we're going to use these conversion factors. And I'll just talk through with you how I set up the problem and what my rationale is. So our conversion factors, we're going to have, the only things that are going to be given is 1 liter equals 1.057 quarts. Yeah. So that's the only thing that's going to be given. Okay, so what we do first, all the time, is the first step is write down your measured number. So write given number. Given number. And the given number that you have to convert is 30. So you write down 30. And always include the unit. And before I continue with this process, this is how the textbook teaches it. If you guys know another way of unit conversion from high school, stick with that. If you get it right every single time, stick with that. Because I know people's minds work differently and you learn things differently. So if you have your own way of doing it, stick with it. As long as you get it right. So 30 mils. Then the next thing is we're going to use our conversions or what we know to get to our desired unit. Now we're getting to quarts. So we all the time, well, most of the time we want to think backwards with what they give us. So quarts, what we have given is 1 liter equals 1.057 quarts. All right, so that means it gives us liters. So we want to get to liters. How can we get from milliliters to liters? Boom. Exactly, divide by 1,000. So that's one of the key conversions that you should have memorized for everything. Is milli to the actual unit, so divide by 1,000. So I'm going to write down the conversion, just have it out here. And these ones wouldn't be given, the ones with the prefixes. So 1,000 milliliters equals 1 liter. So what we're going to do, multiply 1 liter on the top, divided by 1,000 milliliters. And the reason why we do that is we want our destination to be in the numerator. Our destination answer unit in the numerator. So milliliters will cancel out, and we can just continue. So now, whatever this number is, 0.03, will be the liters, that is the 30 milliliters converted to liters. Then we can directly use our next conversion, which is our liters to quarts. So we can put quarts on the top, because that is the unit that we want to end up with, divided by our liters. Liters will cancel out, and your answer will be 30 divided by 1,000 times 1.057, about what, 32 or something? What is it? Oh, this many. That's what I meant. 0.03, whatever. So you get this answer, 0.0317 quarts. So the answer is in 3 sig figs. The reason why it's in 3 sig figs is because our question asked us to convert 30.0 milliliters into quarts, not just 30, it's 30.0. So 30.0 has 3 sig figs. So yeah, any questions on that? Okay. So let's do a more difficult one. What is this? Oh no, the answer is there. Let's do another one. Here, I'm going to do a different one. I'll add one. Okay. So what we're going to do is we are going to convert 15 kilometers per liter into miles per hour. Ooh, double step conversion. What do we do, right? Not that bad. I'm gonna have a comment. fun of me? Oh, no, you're not gonna make fun of me.
How do you get from liters to hours?
Oh, duh. I meant
Seconds?
good one. So kilometers per, I'll do second, yeah. No, meters per, I'll do 15 meters per second, the miles per hour. Sorry about that. 15 meters. Good catch. Don't you know the conversion from liters to hours?
I think Michelle was something like really loud.
I wish I was that cool. All right, when you take points off on exams, all right, you didn't have correct safe space. So the exams are going to be mostly multiple choice, so the answer should be apparent. In the open-ended, there are, well, actually, wait, we're doing online. There isn't any open-ended. The open-ended is graded by Canvas. Try your best. I think it should be good. I could override things, but it should be good in terms of the times. See how you do on the homeworks first. If you're comfortable with the homeworks, the tests are going to be just like that in terms of the types of questions. So I would say it's always good practice to have the correct number of sig figs, because with that correct number, you're never wrong. Even though it does take another second to think about it. Anyway, let's do this. Meters per second to miles per hour. All right, the only conversion that will be given is 1.61 kilometers equals 1 mile. Those of you who run track, you should know that one. All right, so there is actually a complicated way to do this all in like one step even though it's a rate in kilometers per second or meters per second, sorry. But I'm very simple. I'm an idiot. So I like to split everything up into its individual units. So I'm going to look at 15 meters per second as 15 meters over 1 second. And I'm going to individually take these units and convert them to our destination units and redivide them. So I'll do 15 meters first. And we know that we want to get from kilometers to miles. So we need to convert meters to kilometers. So we know that 1 kilometer is equal to 1,000 meters. The meters will cancel out. And then our kilometers, we can go directly to miles with our new conversion. 1 mile equals 1.61 kilometers. Kilometers will cancel in numerator and denominator, and you'll get a number. Does that make sense in terms of the process? Make sense? Okay. All right, so then the next one, someone can calculate this number for me. So the next thing we do is 1 second. We want to convert that into hours. And we're not given conversions, but since we're all in the same time unit system, we should understand this. So to go from seconds to hours, we want to go from seconds to minutes, and then minutes to hours. Oh, it's okay. It's okay, Clay. Don't worry about it. All right, so we're going to go from 1 minute is 60 seconds. Seconds will cancel out, and we can go from minutes to hours. So 1 hour is 60 minutes, and the minutes will cancel out. So then this number will get our hours. 1 second is how many hours? So that's 1 over 3,600. And then what is this number? Does anybody get it? 0.009?
Yep.
Awesome. That makes sense. So we're going to divide this 0.009 divided by 1 over 3,600, whatever that is. So basically 0.009 times 3,600. What is that?
34.
34. And sig fig wise, correct, good, since 15 only has 2. So it would be 34 miles per hour. Decent speed. Cool. All right. So that is one of these two-step conversions. Doesn't really get too much more complicated than that. You can check out the video that I have on Canvas. I went over a complicated one that has like 4 steps, and then one with a rate that has a couple other steps. And it's the same exact process. You want to go from one unit to the next. And a tip when you have like 4 or 5 unit conversions, because sometimes you might have a crazy problem like that. You want to write them all out. And then you'll see which ones you want to use first based on the unit that you're given. So if you're given miles, you're looking at your units and see which one has miles. This one, use it. Then you end up with furlongs. Furlong is a unit of measurement too. Which one of these has furlongs? Oh, this one, I want to use that. Which one has rods or whatever? And you use that in miles and kilograms or kilometers. I'm just saying units right now, but you see what you have and you use it. And it goes very systematically. Yeah. Okay, so any questions on that? And any questions on unit conversion as a whole? Because we're kind of almost done with that. Anything else that's important? Oh, density. We'll talk about that in a second. But yeah, any questions on the ones we just did? From anybody online or here? Okay, cool. All right, so you can also use density as a unit conversion, as a conversion factor. So let's say for lead, we'll skip water. So lead is 11.3 grams per milliliter. So we know that 1 milliliter of lead weighs 11.3 grams, okay? So how much does 4 milliliters weigh? All right, if 1 milliliter weighs this much, you can just multiply it by 4 totally. But the correct way to do it is 4.0 milliliters, and then you're going to use your conversion factor that 1 milliliter is 11.3 grams. So you would do 4 times 11.3 over 1, and you would end up with your answer. Just like this, and your answer is 45. So you can also use density as a conversion factor. Okay, so this is another example. We're not going to go crazy with the examples, but there's another one. I have videos on it already. Not this one, but it's very similar. Units raised to a power. Oh, that's important. So let's do this one. Convert cubic inches to cubic centimeters. And you're only given this, that inches, 1 inch equals 2.54 centimeters. So I guess I don't have to write, it's right there. So I'll just, whatever, it's late. Well, I do want to explain it though. The thing is, they don't work like normal units since they're cubed. So what you have to do is you have to cube the whole thing. You have to cube the whole conversion factor. So you have to cube 2.54, and you have to cube 1 inch. So if you do that math, you get 16.4 centimeters cubed is 1 inch cubed. So for those cubic units, and even if it's square feet, square whatever, you want to make sure you square the entire unit to get the conversion first. Then you can do it normally. So that works. Because they're exponentials when you increase the dimensions. Any questions on that? I'll give you guys a second. Okay. Cool. All right, so here's one. So how many cubic centimeters are in 2.11 cubic feet? Okay, so you're given cubic feet to cubic inches, which you can figure out by just cubing 12. And then you're given cubic inches to cubic centimeters, which we just did. So now you can use those numbers. So you can multiply with your 2.11 cubic feet. You know the conversion from cubic feet to cubic inches, and you know the conversion from cubic inches to cubic centimeters. So you can do a 2-step conversion in this pattern. So you have your 2.11 times your conversion. Here, feet will cancel out. You'll have inches, and then you go right from inches to centimeters cubed, and you get this number. Now, since the number, the original 2.11, has 3 sig figs, then your answer has to have 3 sig figs. So you would use a scientific notation. It can be 5,980, or it could be 5.98 times 10 to the 4, wait, 59,800. It could be 59,800, or it could be 5.98 times 10 to the 4. Each one of those would have 3 sig figs. But the scientific notation one's normally the norm, the better conventional way to do it. All right, any questions on this one? No? Pretty tired? Okay, we did this already. Or we could do this, you can do this one on your own. Just more steps. The equations, let's do this. So I think this 78, what's left? This might be anything else important? No. Okay, so this is the last. I'm going to lecture over again. So we'll do the last, this will be the last problem. And I'll give you one more fun fact to leave off with, and then we're done. Okay, so find the density of a metal cylinder. So density, mass over volume, with a mass of 8.3 and a length of 1.94 centimeters and a radius of 0.55 centimeters. So you have to think a little bit of what you're looking for. So always think about the end goal. The end goal is density. So for density, you need your mass and you need your volume. You have your mass directly, that's great, 8.3. And you have the information required to get your volume. You know it's a cylinder. So, geometry, 9th grade, what do I do? Well, 9th grade, right? You get geometry? Yeah, that's what I did.
I did 10.
10? Okay, I did 9. Yeah, sophomore year of high school, yeah. But that's 10th grade. I'm an idiot. Yeah, so, yeah, 10th grade.
Hello.
Hi.
So for this one, since there's no clear beginning, how many sig figs would you use?
So there's 3 measured numbers there. There's
Yeah.
the 3 and then the other 2. So you would use the one with the least number of sig figs.
Okay.
It would be 2 sig figs because you're 8.3 and you're 0.55.
All right.
Good. So with the volume, you have the equation required. So cylinder, what's the equation? It's radius 2 pi r times the length, right? Yeah. So 2 pi r times the height or the length of the cylinder will give you the volume of it. You take the mass and divide it by that volume. So we can do that. So they did that. They have the volume equals 2 pi r, wait, pi r squared, sorry, pi r squared. 2 pi r is circumference. Yeah, maybe I should go back to 10th grade. Pi r squared times the length gives you the volume. Multiply all those together, then you get the number, you get 1.84 centimeters cubed, and you want to, since this is an intermediate step, you want to have the correct number of sig figs. So our answer, and that was a good question that you asked online, was that how many sig figs should we use? And the answer is 2, because our grams and our radius have 2. So the volume here would be 1.8 centimeters cubed. So then you want to take the mass and divide it by that. And you take the mass 8.3 divided by 1.84, whatever, 1.8 really, and you get 4.5, and your answer should be 4.5. And that's it. Grams per centimeter cubed. Okay, any questions on that? I'll give you guys a second. That's a little bit more complicated, but they're not going to get more difficult than that. So your homework does have some crazy ones. Not crazy, but just a little bit more difficult. But it's good for you to work them out, because if you get those, then you'll understand the tests and everything that's thrown at you. Okay, so I'll leave you off with one fun fact. So it's a common, so you hear like the flat earthers, right? It's the crazy people that think the earth is flat still. So, and then some people say, well, technically, Earth isn't technically round. It's like a pear, or it's like weird. It's like a ellipsoid or something. No. So the Earth is almost a perfect sphere in terms of its smoothness, and it's well, in our eyes. So if we, and you think, oh, there's like mountains and stuff, it's all misshapen is like volcanoes and stuff, right? Okay. But if you were huge and like, if the Earth was a, like a cue ball, a pool ball, and you were to hold it, it would be smoother than the smoothest cue ball ever manufactured, smoother than the smoothest anything ever manufactured. The reason why is because if you do the math behind it, so the tallest thing on Earth, the tallest place on Earth is not Mount Everest, it's like K2 in Nepal, right? That is, I think, about a mile or so, maybe 2 miles, maybe 2 miles. Let's say it's 2 miles, 10,000 feet. So that's the highest. The lowest place on Earth, let's say drain all the water, lowest place on Earth is the Marianas Trench in like the Pacific, right? That's like a mile deep. So the highest point to the lowest point in Earth is 3 miles, that's a rough estimate. The circumference of the Earth, and even the circumference of the Earth is like 80,000 miles or something like that?
That was like 24,000.
24,000, whatever, 24,000, still a lot, right? A lot of miles. So let's say, and the radius of the Earth is probably 8,000. So let's say the radius of the Earth is 8,000 miles. Double that is 16,000, that's the diameter. So 3 miles divided by 16,000 miles is less than 1%. So that means, on average, the Earth at really every other point is more than 99% smooth, because the difference of the lowest point and the highest point as a percent of the entire diameter is less than 1%. So overall, it is extremely smooth, and we can't detect that by touching it or by looking at it. So Earth is really like Earth is a ball. I'm done. Thank you. All right, I'll end with that. Okay. Oh, there's a question by Josh. So for the last part, if you divide just by 1.8, I found that it's over 4.6. So would you round to 4.6, not 4.5? Oh, yes. Oh, that's a good question, actually. So you get 4.6.
Well, no, that's because you divide by just 1.8, but you divide by the pound.
I don't think you're supposed to do that. You're supposed to do the whole.
Yeah, you're supposed to keep the whole number.
Yeah.
Right?
So,
That's kind of nice.
Yeah.
So you figure out the
That's
end.
what they told me in high school.
okay, so in high school, good discrepancy. All right, so in high school, they tell you to round at the end. In physics, they tell you to round at the end. That's how you get sometimes. I don't know about this physics, but they should tell you to round at the end. That's the best way to get the answer. But in chemistry and the hardcore sciences like this, where the measurement significant figures matter, it's weird because you're measuring numbers. So for this case, the volume should actually just be 1.8. And this answer I think would be 4.6 then.
Yeah.
So this isn't exactly right. You have to do your sig figs in each step, because the 0.55 and the 1.94 are measured. They're measured numbers. So you have to go by sig figs, by using 2 sig figs for that answer. So yeah, I hope that answers your question. So I think it would be 4.6. Yeah. Okay, I'm gonna end the recording.
But just 4.6